9 minutes ago, in terms of how long light takes to reach us from where it actually happened, is not quite right for this story, but close enough, because right now, more than 24 billion kilometers from Earth, Voyager 1 is sitting inside a region of space that genuinely does not match what physics predicted it would find there. Not science fiction, not a conspiracy theory, actual instrument readings sent back across more than 22 hours of travel time, describing a place that theoretical models simply did not see coming. So what exactly did Voyager find out there, and why are scientists still trying to explain it nearly 5 decades after this spacecraft first left Earth on a mission that was only ever supposed to last a few years? Let's rewind first, because to understand why this matters, you need to understand what Voyager 1 actually is. Launched in 1977, it was originally built to fly past Jupiter and Saturn. I snapped some photographs and probably shut down not too long after. Nobody seriously expected it to still be transmitting data back to Earth nearly 50 years later. And yet, here it is, humanity's most distant working spacecraft, drifting further into the darkness every single day, long after it finished the mission it was actually designed for. Along the way, it delivered some of the most iconic images in the history of space exploration, close-up views of Jupiter's swirling storms and Saturn's intricate rings before engineers made the decision to keep pushing it outward instead of shutting it down once those flybys were complete. That choice, made decades ago by scientists who had no idea Voyager would still be functioning today, is the entire reason we now have a working spacecraft sitting in a region of space no other human instrument has ever directly sampled. In August of 2012, Voyager 1 crossed something called the heliopause, the outer edge of a massive bubble of charged particles blown outward by our sun, known as the heliosphere. Crossing that boundary meant Voyager 1 officially left the solar system's direct influence behind and became the first human-made object to enter true interstellar space, the vast region between stars. For decades before that crossing, physicists had a fairly confident picture of what this boundary should look like. A clean, sharp line, solar wind on one side, cold interstellar, medium on the other, with a dramatic shift in conditions the moment you crossed from on E into the next, almost like walking through a doorway from one room into a completely different one. That is not remotely what Voyager 1 actually found. Instead of a clean boundary, Voyager's instruments detected something researchers nicknamed the Wall of Fire, a thin, superheated layer sitting right at the edge of our solar system with temperatures estimated in the tens of thousands of degrees, in some readings pushing toward numbers around 30,000 to 50,000 Kelvin. On paper, that sounds like it should have vaporized the spacecraft instantly. In reality, Voyager sailed through completely unharmed because temperature and heat are not the same thing out there. Interstellar space is so thin and empty that even though individual particles are moving at blistering high-energy speeds, there simply aren't enough of them close together to actually transfer that heat into anything solid, including a spacecraft built decades before anyone knew this region even existed. Picture E standing next to something registering tens of thousands of degrees and walking away completely unharmed, simply because the particles carrying that heat are spread so far apart out there that almost none of them ever actually collide with anything solid enough to feel it, no matter how fast any individual particle happens to be moving. It's a genuinely strange kind of hot heat with almost nothing behind it to deliver the punch. More like standing in a room full of scattered blazing embers spaced meters apart than standing inside an actual fire. Then came the magnetic field problem, and this one genuinely confused researchers for years. The leading models before Voyager's crossing predicted the magnetic field direction should shift noticeably once you left the sun's influence and entered true interstellar space, since the galaxy's own magnetic field should point in a meaningfully different direction than the sun's. Instead, Voyager 1 measured a magnetic field on the interstellar side that stayed strangely aligned with the one inside the heliosphere, barely shifting direction at all across the boundary. That single reading quietly undermined a chunk of existing theory about how sharply defined our solar bubble actually is, and suggested the edge of our solar system might blend into interstellar space in a far messier, more tangled way than anyone had modeled. Some researchers have compared it to a rubber band, stretched and deflected around a beach ball, with the sun's magnetic field getting dragged and reshaped as it presses up against the wider galactic field, rather than simply stopping in a clean line the moment it meets it, the two fields blending and bending into each other instead of snapping apart at a sharp, obvious edge. Scientists now believe Voyager 1 may still be sitting inside a distorted transition zone, rather than a truly pristine, undisturbed patch of interstellar space, and some predictions suggest it could take another decade or more of continued travel before its readings finally settle into something closer to the galaxy's true, undisturbed magnetic direction. On top of that came a plasma density puzzle. Well, it was once Voyager 1 crossed into interstellar space, scientists expected plasma density readings to behave in a fairly predictable, steady pattern. Instead, over the years since crossing, Voyager's instruments have recorded plasma density and magnetic field strength quietly climbing, hinting that the spacecraft might be moving through an unexpectedly denser, more structured region of the interstellar medium than existing models anticipated. Researchers studying this data have openly said they didn't expect this much day-to-day and year-to-year change UDT there. One scientist working closely with Voyager's cosmic ray data admitted he assumed conditions in interstellar space would basically stay the same day after day, and that assumption simply did not hold up once real numbers started coming back. If confirmed and better understood, this rising density could mean Voyager 1 is approaching, or has already entered, some kind of previously unmapped structure with I and the interstellar medium. A pocket of space with its own distinct properties, rather than one smooth, uniform void stretching endlessly between stars, more like a patch of weather than a fixed, unchanging emptiness. Cosmic rays added their own twist to the mystery. When Voyager 1 first crossed the heliopause, researchers recorded a sharp spike in low-energy, galactic cosmic rays arriving from deep space, paired with an equally sharp drop in the anomalous cosmic rays generated closer to our own sun. That part matched predictions reasonably well. But then, Voyager's instruments picked up something models had not accounted for, an unexpected unevenness in how those cosmic rays were arriving, stronger from some directions than others relative to the surrounding magnetic field, a pattern that hinted the local magnetic structure out there is more tangled and directional than the simple, smooth picture scientists had originally imagined. In other words, cosmic rays weren't arriving evenly from every direction the way a truly uniform, well-mixed region of space would produce. They were arriving in an uneven pattern that only made sense if the magnetic field itself out there had its own hidden shape, folds, and channels that no model had accounted for before Voyager actually flew through it and measured it directly. And then, more recently, came something almost poetic. Researchers analyzing Voyager 1's plasma wave instrument picked up a faint, continuous signal researchers described as a kind of hum, a steady, low-level vibration in the interstellar plasma surrounding the spacecraft. Before this discovery, scientists mostly relied on occasional shockwaves, triggered by solar outbursts, to measure plasma density out there. Brief, dramatic spikes similar to catching a lightning strike during a thunderstorm. This newly detected hum gave them something completely different, a persistent, gentle signal researchers, compared to a steady rainfall, letting them track the density of interstellar plasma continuously, even during the long, quiet stretches between solar disturbances. IIST is, in a very real sense, the sound of the space between stars, something almost nobody expected Voyager's aging instruments to ever pick up this clearly, this far from home. Scientists involved in this particular finding described it almost poetically, saying it felt like picking up the faint, persistent hum of interstellar gas itself, a signal so subtle it had likely been sitting there the entire time, simply waiting for an instrument sensitive enough and quiet enough to actually notice it, buried underneath decades of noisier, more dramatic readings. Here's the part that makes all of this even more remarkable. Voyager 1 is not exactly running on cutting-edge hardware. It launched with computing power that today feels almost laughably primitive, and after nearly 5 decades in space, its plutonium power source has been steadily, unavoidably fading. Engineers have had to make difficult choices, quietly shutting down individual instruments one at a time, prioritizing which experiments stay powered on as the spacecraft's energy budget keeps shrinking. Every single discovery we've just walked through came from a machine that is slowly, deliberately being asked to do less and less just to survive a little longer out there. In one recent episode, mission engineers even noticed Voyager 1's power levels dropping unexpectedly after a routine maneuver, and had to scramble to work out a fix before the spacecraft lost too much capability to keep communicating with Earth at all. Every additional year of data we get out of Voyager 1 at this point is less a guarantee and more a small, hard-won miracle, squeezed out of hardware that was never built with anything close to a 50-year mission in mind. So why does any of this matter beyond simple curiosity? Because Voyager 1 is currently our only direct physical sample of what interstellar space actually behaves like, rather than what our models on Earth assume it should behave like. Every unexpected reading it sends back forces physicists to revise their understanding of the heliosphere's true shape, how sharply or messily it blends into the wider galaxy, and how our sun's magnetic influence genuinely fades into the darkness beyond it. These aren't small footnotes either. They directly shape how scientists design future interstellar missions, what kind of shielding and instruments those spacecraft will need, and what kind of environment humanity's next deep space explorers should actually expect to encounter once they cross that same invisible line, decades or possibly generations from now. It also matters for a much simpler reason. Every model of the heliosphere we build here on Earth no matter how sophisticated the mathematics behind it, is ultimately a guess dressed up in equations until real spacecraft data comes back to confirm or contradict it. Voyager 1 is currently the only tool checking that homework at the actual edge of our solar system, and so far it keeps handing back answers that don't quite match what was written down in advance. Voyager 1 isn't entirely alone out there either. Its twin, Voyager 2, launched just weeks earlier in 1977 and took a slower, more roundabout path through the outer solar system, eventually crossing into interstellar space itself in November of 2018, 6 years after its sibling. Comparing readings from both spacecraft, entering interstellar space from slightly different directions and at different times has given scientists an even richer picture of just how uneven and directionally dependent the true edge of our solar system really is, rather than relying on a single data point from a single direction in space. And that comparison is exactly what first revealed how unevenly shaped and unpredictable the true edge of our solar bubble actually turns out to be. There is something quietly humbling in all of this too. We built detailed mathematical models of the edge of our solar system decades before we ever had a real spacecraft out there to check them against. And when we finally got that real data, reality simply refused to match the paperwork. Not because the scientists were careless, but because no model built entirely from theory and distant observation could ever fully capture the actual messy texture of a region no human instrument had ever physically touched before Voyager arrived. It's a reminder that even our best physics is still, in some sense, a map drawn from a distance, and maps only ever get truly accurate once someone actually walks the territory themselves. And Voyager 1 keeps going. Slower now in terms of new instruments coming online, but still transmitting, still drifting further outward every single day into a region of space that remains stranger and more dynamic than anyone predicted back when this spacecraft first launched in 1977. On board, it still carries the golden record, a phonograph disc etched with sounds, images, and greetings from Earth, tucked away in case some future intelligence ever encounters this small, aging machine drifting silently through the galaxy long after its power finally runs out, and it goes quiet for good, carrying a message from a species it will likely outlive by many thousands of years. Nobody knows exactly how many more surprises are still waiting out there in the data still to come, or how many more years this aging machine has left before that day arrives. But for now, nearly 50 years after launch, it is still doing exactly what it was never really designed to keep doing this long, quietly rewriting what physics books say about the true edge of our solar system. If this kind of real, verified space mystery is the kind of thing you want more of, go ahead and like this video and subscribe so you don't miss the next one. Which part of Voyager's reading surprised you the most? The wall of fire, the aligned magnetic field, or that strange interstellar hum? Drop your answer in the comments, because honestly, even scientists who work with this data every day admit they're still trying to fully wrap their heads around it. And there's something oddly comforting about a 50-year-old machine still humbling all of us this far from home.